Okay, welcome. This is Wednesday, November 18 class session, and we seem to have everything in order today. Over the last week or so, I'm just still admitting people into the room. Over the last week or so, both the Zoom software and Apple Computer released an operating system update. Zoom software released upgrade to its software. It might not be a bad idea for you to re-download the Zoom software that you're using on any device. I mean, sometimes your devices automatically update things, but I had some issues where I just had to physically re-download the software and have it reinstalled, which wasn't a significant problem, but it just restored a few things that got broken. So sometimes if you see something happening different or unusual, then reinstalling software is not a bad idea. Zoom did add a few other features to its software that I had to navigate. Okay, let's talk about what we're going to do today. And what we're going to do today is kind of practical and fun. It's called the law of sines. We are operating. Let me show you our webpage. In week 12, and we're getting along towards the end of the course. We talked about graphing parametric equations last time. We talked about the law of sines today and the law of cosines next week. Pay attention that next week we do not have a scheduled class meeting on Wednesday. In the Thanksgiving week, Delta College always has Monday, Tuesday classes and always cancels Wednesday, Thursday, Friday classes. And they're just going to continue with that procedure. Let me get someone else in the room here. They're continuing with that procedure this year as well. So our class meets Monday, Wednesday, but next week it will only meet on Monday. I'll have office hours on Monday and Tuesday as usual, but on Wednesday there are no classes scheduled and no office hours scheduled for the Thanksgiving break. So what we're going to do over the next two class periods, the law of sines and the law of cosines, it's kind of a practical, fun application of solving triangles that are not right triangles. And that'll compose the whole of what we're doing for those 2 weeks. Now, just to pay attention to your homework, you submitted a homework last night, and you have another homework assignment now posted. Notice that's due on Tuesday, November 24, which is a day of classes next week at the college. So I still have assignments set for you to hand in on Tuesday, November 24, even though we have no class on Wednesday, November 25. So you're just looking ahead at your assignments in week 12 and week 13. Then you can look into those assignments right there. Just as a cosmic scheme of things, look to our resources page where we list all assignments and all handouts we give. We're coming towards the end of the assignments here, and then we'll help you prepare for your second exam. So I have written homeworks for you, 10, 11, and 12. And we're opening up today, chapter 7. And then chapter 8, and that is the entire course. And then we don't have a homework due in the last week because basically I'm asking you to prepare to do your exam. And as we've stated already, I anticipate the second exam should look very similar to the first exam, similar in length and content, I haven't written the second exam yet, but as we get closer, you can ask questions about that. Okay, let's go back to week 12 here. So today we're looking at the law of signs and what people call the ambiguous case. And I can explain that pretty directly. And then we can do these calculations. Okay, got the videos from the classes up. Yeah, it was in a couple of classes, yours and someone else's, where I had issues with the video recording that I've since fixed. But I may have recorded 90 minutes of just my name or my icon. Now remember, you have notes from each class session posted. So even if I screwed up the video, you could theoretically listen to the audio and follow along in the class notes that we post. So we got kind of a backup system in that way, although it's not perfect, but we're doing what we can. Okay. Also remember, don't forget that we have office hours posted before class, each class day, and office hours also posted Tuesdays, Thursdays. People from various classes pop in there and ask questions. And we just help people first come, first serve. You're welcome to come in there anytime and ask a question. Okay, let's get started with the law of signs. And this is something that's also very practical for your calculator. So today, when we work on solutions of triangles, we're often going to be estimating. We're often going to be approximating, and then we'll follow the instructions for approximating given in a particular problem. So how can I explain the law of signs to you just in a very straightforward, generic way? You're used so far to the idea that if someone gives you a right triangle, they're giving you quite a bit of information. There's only 3 angles in a triangle. And in a right triangle, one of them is 90 degrees. That automatically means that if I gave you either angle remaining, for the moment, let's call them angle A and B. If I give you A, you can find B. If I give you B, you can find A. So having one triangle, having one angle of the right triangle already specified is a big, big bonus. Second bonus in a right triangle is that the 3 sides are not independent. That if you know 2 of the sides, you can figure out the 3rd side by the Pythagorean theorem. Let me label this 3rd side in the triangle C. It's kind of traditional to use the capital letters A, B, and C for the angles of a triangle. And in particular, when you're talking about a right triangle, it's kind of traditional to use the angle C to be the right angle. Here's another tradition we're going to focus on today and next week. Traditionally, some people label the sides of the triangle with lowercase letters A, B, and C, opposite the angles capital A, capital B, capital C. And the reason for that is in a very strong way, the sides opposite the angle are paired with the angle. That is the mission of the law of signs. It's a very beautiful and very effective rule. So people get in the habit of naming an angle with a capital letter and then naming the angle opposite or the side opposite that angle with a lowercase same letter. Now you could say X, Y, and Z and lowercase x, y, and Z. You could say P, Q, and R and lowercase p, q, and R. But follow this convention. Don't label an angle capital A and then label the side opposite at B or C or D or H or something. So follow this convention. You don't have to put the A, B, and C in a particular order, although with a right angle, you traditionally refer to that as C because you're used to using the Pythagorean theorem and writing the Pythagorean theorem like this. So I summarize that just in this short phrase. A right triangle has many advantages. If I give you just a little bit extra information, I'm specifying the whole triangle. Now, what happens if the triangle is not a right triangle? I mean, for example, I can say right here that the sine of A is lowercase a over lowercase c. That's called right triangle trigonometry. But what if the triangle is not a right triangle? Let's draw a triangle A, B, C, like this. If at all possible, when you draw a triangle, make one of the sides horizontal, kind of even with the horizon. But neither one of these angles is a right angle. This is not a right triangle. And so I'm just going to label the two angles B and C in any order I please, and then label the sides lowercase a, lowercase b, and lowercase c. It's really important that you recognize the difference between a right triangle and a non-right triangle. You cannot say that the sine of A here is A over C or A over B. This is not a right triangle, and neither A, B, nor C is the hypotenuse of a right triangle. So often you've been drawing triangles for me and sometimes drawing triangles that are not right triangles, and then just saying opposite over hypotenuse, calling it sine, but you had no hypotenuse. So you have to treat a triangle that's not a right triangle in a different way. I also had many cases throughout the first couple weeks of the course where people were using and quoting from our formula sheet the law of sines and law of cosines, probably because you've seen them before and used them before. But if you're in the context of a right triangle, the law of sines and law of cosines is kind of overkill and perhaps even wrong or misleading. So I respect the fact that you may have seen the law of sines and cosines before, and for those of you who haven't, we're going to explain them now. But you can't use them in a context where they don't make sense. So you have to make sure every rule for its place, every technique for the moment that it's necessary. So today we'll explain what it means to say law of sines and law of cosines. So if I can't talk about the sine of an angle A as if I was doing a right triangle, then what would be the best I could do in a picture like this? Now I could draw on this picture right here, but it's kind of small. So I'm going to super enlarge it down here just to give us room to draw. Let's make a large triangle here. If you're practicing drawing too, you could make a large triangle on your paper of any dimension you wish. But I'm just going to draw it like this. And here I have a triangle with three different sides and noticeably different length sides. You can pull out a ruler, but I think you can see they have different length sides. And none of these angles is a right angle. So I can't just say, oh, this side over that side, cosine, this side over that side, tangent, sine, cosecant, secant, cotangent. It just doesn't work like that. But instead of focusing on what I can't do, let's think about what I can do. I label my sides lowercase a, lowercase b, lowercase c. You know, the only trouble with labeling things with the lowercase letters is I admit that sometimes it's hard to tell the difference between an uppercase C and a lowercase c. So just focus on making your uppercase C's for angles larger than your lowercase c's for sides. Or you can put a little curly Q on the C for the angle or something, whatever it is that helps you keep them straight. Otherwise, when you're writing on your paper, you'll forget whether you're writing uppercase C or lowercase c. So first, let me introduce the vertical altitude in this triangle. The triangle I drew for you in green is not a right triangle, so I can't use the sine, cosine, tangent traditionally on that green triangle. But what if I just put a little altitude, a vertical wall from this horizon side, AB, up to the point C? Notice I created two right triangles when I did that. Two different right triangles. And let me call this side length. A traditional letter is H for height. Could be the height of a building, could be the height of a tree, could be the altitude of a plane. But when I specify that H, it relates the angle A and B in a special way. So think about this. Now that I have a right triangle here with HC partially and B, well, I don't know how much of C I'm using on the left and how much of C I'm using on the right. But then let's just focus on the H and B. In this right triangle, the ratio of H to B is the sine of A. I am allowed to quote the trigonometric ratio for that right triangle. Likewise, the ratio opposite to hypotenuse, here the hypotenuse would be the A on this side of the triangle, H to A is the sine of B. And that relates A angle and B angle. If you think about it like this, H is now equal to B sine A, but in the triangle on the right, H is equal to A sine B. That means I can set those two things equal to each other. If B sine A is H and A sine B is H, now notice I say A sine B without saying lowercase a sine capital B. I'm taking it for granted that you visually see and know the capital letters refer to angles and lowercase letters refer to sides. Get used to that convention. But these two things are both equal to H, so I can set them both equal to each other. So B sine A is the same as A sine B. Or written in another way to keep the matching letters together, what if I divided both sides by A and divided both sides by B? That's the lowercase a, the lowercase b. Then I have this expression. Sine of A is to A as the sine of B is to B. Now this is the beginning of what people call the law of sines. In fact, the law of sines relates all three angles, and I can write as well, sine of C is to lowercase c. Now you don't know what good these are yet. Okay, you don't know how good this relationship is yet, but this is a legal relationship now. You say, how did you get the sine C over lowercase c in there? And I say, well, let's just develop another altitude. What if I extended this side and drew a perpendicular from B to that side. I kind of have to stand up and look over my paper to do that decently. So excuse me if I'm blocking the light slightly. Let's look at this right triangle here. That I got from extending the side B through the angle C and drawing perpendicular to the angle B. Let's call this capital H right here. This is height, but height, if I look at the triangle from a different perspective, let me pick up the paper for a second. See, that would be height if I'm looking at the triangle from this perspective. But that would get a little dizzying. So let's go back to vertical here. What can I say? This height relates. This height relates the angle A to the angle C. You say C is over here and H is over here. How does that work? But first of all, let's draw the sine of the angle A. It will be H over C. Right? This will be the opposite side in the right triangle. This will be the hypotenuse of angle A in the right triangle. Now let's look at angle C. Now angle C has a supplementary angle here, and this angle has a sine of H over A. But you say that angle with the double bars is not C. But remember, you have an identity for the sine that says for a supplementary angle, the sine of angle A is always the same as the sine of 180 minus A. That's one of your identities. So if the sine of 180 minus A with the double bars is H over A, that's also equal to the sine, sorry, I'm using letter C here, my fault. That's also equal to the sine of C. So capital H is both C sine A and A sine C. Again, I can match the letters and write that as sine A over A is equal to sine C over C. First uppercase C, then lowercase c. So since sine C over C is sine A over A, I can tag that on to the back of this relationship. And these three ratios together are called the law of sines. Let me show you how we can use that, and we'll pick out a particular problem. We'll just take some problems out of the book. So for reference, I'm just going to write this at the top of the paper before we work out any particular problem. This is the law of sines. And it basically says in any triangle, it doesn't have to be a right triangle, the ratio of the sine of an angle to the side opposite is the same for all three angles. And so that's a powerful tool for calculating. What would happen if I gave you a triangle? And let's just do a starter triangle right here. Let's say this is 10 units long. And let's say this angle right here is 25 degrees. And let me give you another angle right here. Let's call this angle 40 degrees. Can you work out the remaining sides and the remaining angle of the triangle? I put that 25 in an awkward place. Let me move it to the inside. And let me label these sides in the traditional way we've described labeling them. Let's call this angle A. Let's call this angle B. Let's call this angle C. That makes this side lowercase a. That makes this side lowercase b. And that makes this 10 side lowercase c. Now you're given three pieces of information. You have two angles here, and you have this side between the two angles. And you have missing pieces of information, these two sides and this remaining angle. But you can fill in the information missing from your knowledge of general triangles and this law of sines. For example, A plus B plus C has to equal 180. And if that's the case and you know A and B, then you can find out what C is. So 25 degrees plus 40 degrees plus C is 180. So this is 65. Subtract 180 minus 65. Then you get C is 115 degrees. I haven't necessarily drawn this beautifully. Like, is this really 40 degrees? Is this really 25? But if you assume that this is 25 degrees and 40 degrees, then the remaining angle has to fill up the rest of the 180. 65 plus 115 is 180. So that makes this angle, I'll choose a different color, 115 degrees. Different color doesn't show up on the camera. It will show up when I scan the pages. How am I going to find these two sides, A and B, if I can't use the Pythagorean theorem? Well, now that I know all three angles, I can take the side I do know, which is side C, and create ratios to give me sides A and B. So right here, I will say the sine of 115 degrees is to 10 as the sine of 25 degrees is to A. And that's the same as the sine of 40 degrees is to B. Now, if I take these both one at a time, this will let me find out what A is and find out what B is. So when I cross multiply in the first term, A sine 115 is 10 times sine 25. And that means A is 10 sine 25 divided by sine of 115. I'm talking about degrees here. I could use radians. We're commonly calculating degrees. Now, how about the other ratio? I could say sine of 115 is to 10 as sine of 40 is to B. So if I cross multiply there, I get B sine 115 is equal to 10 times sine 40 degrees. And then I find out what B is by, again, dividing by sine 115. Sorry, let me erase my paper. 10 sine 40 over sine 115. Now, there's no guarantee that these numbers are going to come out to be simple or pretty. So we'll have to make some reasonable approximation, right? Look to the problem and use the approximation precision that the problem asks you to use. But what if I just simply say here, let's calculate to the nearest tenth for side length. So usually someone's going to give you a reasonable precision what they want. And I'm just going to type these numbers in and round to the nearest tenth. Clear. Sine wave from last time. Clear. Y equals clear, 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 clear. Get out of there. Make sure I'm in. Sorry, get this on my screen in front of you. Make sure I'm in degree mode since I've been talking about degrees. So I'll switch over to degree mode. Thank you. And now type in these two numbers. 10 sine 25 over sine 115. Oh, make sure you close that sign before you do the division. So you type in everything correctly, you know you're in degrees, and this answer is 4.7 units. I didn't attach any units to the problem. Look to the problem. Let's say that I'm going to talk about feet as my units. Then this would be 4.7 feet. Use whatever units they give you to use in the problem. The second number is a 10 sine 40 over sine 115. 10 times the sine of 40, close the parentheses, divided by a sine of 115. And that turns out to be 7.1 to the nearest tenth. Now you could make it more exact if people asked for more precision, right? But to the nearest tenth of a unit, this side is 4.7 feet. And this side is 7.1 feet. So you've solved a non-right triangle with this relationship called law of sines. Now, what we have to be careful about here is that when you're specifying triangles, it matters what sides you use and what angles you talk about. So think about the last triangle. That we gave you right there. We gave you a stick that was 10 feet long. And then we gave you an angle to build from that stick of 25 degrees. And we gave you another angle to build from that stick of 40 degrees. Now, once I specify that middle length and these two angles, well, think about the remaining two sides. They have no freedom in which to meet. They have no two ways to meet. I just extend this side along the 25 degree angle. I extend this side along the 40 degree angle. And then they've got to meet at that location. So the 4.7 side length, 7.1 side length, and 150 degree angle, they were forced on you. You didn't have any choice once I presented a side and an angle at either end of the side. This is called the situation angle, side, angle. And when someone gives you 3 pieces of a triangle, angle, side between, and other angle, 2 angles with a side in between, this is one and only one possible triangle. You don't have any freedom in the other 2 sides and the other angle. You just have to calculate. Let's try it again. What if I gave you an angle and then forced you to accept 2 sides? What if I gave you an angle of 20 degrees and then forced you to accept 2 sides on either side of that angle? This situation is called side, angle, side. And when you think about this picture right here, again, you have no freedom for the third side of this triangle. You're stopping right here after 13 inches, 13 feet, 13 whatevers. You're stopping right here after 7. These 2 sides are fixed at this angle 20 degrees. You can't stretch them out or in any better than that. And that means this side here is forced upon you. I don't know what it is yet, but it's forced upon me by these 2 sides in this angle. Now, as it happens, I'm not able to do anything with the law of sines in this case. For example, let's call this A, B, and C. Let's call this side B, 7, C, 13, and the A unknown. Even though I know I only have one possible triangle I could look at right here, do you see my problem? I have sine of 20 degrees, A is 20 degrees over A, equals the sine of B, unknown, over side 7, equals the sine of C, angle unknown, over the side 13. The law of sines is still true, but I've got a missing piece in each ratio. And so I can't do anything to tell you the remaining information in this triangle. I need another weapon. And that other weapon is going to be next week. So to solve this triangle, I need the law of cosines. To solve this triangle, we need another tool. Which is called the law of cosines. But I do want to put this in your mind. Whenever I specify an alternating list, angle, side, angle, or side, angle, side, whenever I specify 2 angles and the side in between, or 2 sides and the angle in between, then the triangle is uniquely and completely determined. And I have no freedom for the remaining sides and angles. These triangles, I say, are specified precisely, specified completely, if you'd like to use it that way. But you're saying to yourself, well, every triangle is specified completely. Every triangle is specified precisely. No, not necessarily. Let's think about this if I didn't alternate the sides and the angles. And this is what we're talking about today. These are called the ambiguous cases. I'm just labeling my papers here. Good. Got it. So what if I gave you an angle like 50 degrees, and then not the two sides that surround the 50, but the two sides that follow the 50. Let's call this side 100 feet. And let's call this side 20 feet. Sorry, 20 feet, 100 feet. In some sense, I made that picture too small, but I want you to use your imagination. I have a crane that's 100 feet long, and this crane has been cranked up, elevated to 50 degrees. And then I have a rope or a bar, let's say rope for the moment, on the end of that crane that's only 20 feet long. What are you feeling about that rope? You're feeling that rope is not going to touch the ground. So if I give you a triangle with an angle followed by a side, I might be creating a triangle and I might be creating nothing. Think about that. If I have 100 feet on this 50-degree crane, 20 feet is not going to be good enough to reach the bottom. This may not specify any real triangle. Now I see I got an odd acronym right there. Sometimes people would probably rather write this side angle to avoid the strange spelling. But I don't care what order you put these letters in. See, the problem is if you don't alternate the sides and the angles, you might get caught with no triangle at all. Let's try it again. What if I have this crane elevated to 50 degrees? And let's keep the crane at 100 feet long. But now let's set the rope on the end of this crane to be 90 feet long. Let's dangle a 90-foot rope from the end of this crane. Now you can kind of visualize what's going to happen there, and we can check out for sure if you like. But 90 feet long, that's nearly 100 feet. You know that 90-foot rope might stretch over here. I'm going to make this side not as long as the 100 feet, but nearly as long as the 100 feet. And there's one possible triangle, but I could also stretch that 90-foot long rope to the base of the crane as far as I can. And here's another triangle with the same angle and the same side followed by the same side. I'll use a single punctuation mark for feet. Sometimes people use that for minute or for feet. So here, when I gave you angle side, Angle, side, 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 angle, whatever way you want to politely express it. Here I have two possible triangles. Here I had no possible triangle. What about a third case? What about a third case that splits the difference between no possible triangle and two possible triangles? How did I spell possible? There. What if I have my crane elevated at 50 degrees? I'm trying to draw the same 50 degrees each time, but I'm not excellent at that. And the same 100-foot long crane. But what if the rope that I put on the end of the crane is just long enough? Just long enough to touch the ground, perfectly perpendicular. You know what? That would make a right triangle. And because it's a right triangle, I could use my right triangle trigonometry to find out how long that rope would be. Let's do that. The sine of 50 would be h over 100. And I can only say that because I've got a right triangle. That means that h over 100, sorry, I didn't mean to write h over 50. That means that if I multiply both sides by 100, the h is 100 sine 50. Now, let's just do approximately what 100 sine 50 is. It's probably not a common number, right? It's probably not a sweet number. So I'm going to do 100 sine 50. Got it? I already know I'm in degrees. It says the altitude of that crane above the ground, the tip of the crane, is about 76.6 feet. Well, now all three of these pictures make sense. If this altitude is 76.6 feet, well, then of course I could draw two triangles if I pull the 90-foot rope one way or the other. Of course, a 20-foot rope is not going to touch the ground and give me any triangle. Now there's one more case we have to worry about. So you can always find the altitude of the crane, so to speak, and then realize which case you have. But what if I give you one more case? Let's say I am raising the crane at 50 degrees. And the crane is 100 feet long. But this time, I give you a 200-foot rope. Well, now what kind of possibility do I have? The 200-foot rope is not going to go straight down and touch the ground. Well, it's going to go straight down, touch the ground, got a lot left over. Can I stretch the 200-foot rope to the base of the crane, underneath the crane? No, still lots of rope left over. In fact, if the rope is 200 feet and I pull it out to its full length, it's going to be somewhere over here. Maybe that's 100. Maybe that's 200. Sorry. And that extends this distance quite a bit. So it could be, now remember, this crane is still 76.6 feet approximately off the ground. But now this rope is so long that I only have one possible triangle. When you're doing a problem like this, think about the analogy of a crane and a rope. The rope might be too short to touch the ground. The rope might be long enough to touch the ground in two places under the crane. The rope might be exactly as long as is needed to touch the ground only once, or the rope might be so long they can only touch the ground if you swing it way out to the side. Of course, swinging it way out to this side is not going to give me a triangle because I got to complete this green-sided triangle here. Okay, so these are called, well, every one of these is specified, but together, when you give two sides and an angle, you have to choose between multiple possibilities. So these are called the ambiguous cases. Now, the best way to illustrate this is just to do some measurements. Now, I also wanted to illustrate this with a toothpick. I don't know if this makes it better or worse, but let's say I've got toothpicks of 3 different sizes right here. So it could be that if I don't raise my crane very high at all, I could put the toothpick there to complete the triangle, or I could swing the toothpick this way and extend this side to make a larger triangle. But if I raise that crane too high, and this third side, which represents the rope, is not long enough to reach the ground, then what? I have no triangle, no matter how I swing that rope. Likewise, if my crane is kind of short and the rope is very long, the only way to complete this triangle is to pull the rope way out to the side and extend the length of the ground over here. That's why I always like to write one side on the ground, because the ground is like infinitely long. It can make any triangle I like. Okay, let's try this with just some numbers specified to us, and we have to decide which picture we have. So let me pop open the book right here, and I'm in section 7.1 and 7.2. And I won't tell you where I'm taking the problem from at first. I'll just say, you tell me if we can make a triangle here. I'll give you some information. You tell me if we can make a triangle. So I'm going to pick out A, B, C, little a, little b, little c. Whenever you write a general triangle, write down the 3 angles, write down the 3 sides, fill in what you're given, and see if you can complete the rest. So in this problem that I'm looking at, A is 5 degrees, and C is 125 degrees. And C, the side, is 51 yards. Now, is this a legitimate triangle? Is this going to be a legitimate triangle? Now, I have to draw this triangle in some orientation, right? So I'll let you choose the orientation we're going to draw this, but I have this habit, excuse me, let me get me focused on my paper. I have this habit personally of always starting with A in the lower left-hand corner. As long as you draw the thing legitimately, as been described, you can put the A's and B's and C's anywhere you want, as long as they match. So you're talking about an A, an angle A, and I'll write the side here, and I don't know how long it is yet, so I'll just let it go. I'll cut it off in a second. An angle A of 5 degrees. So this is a very slight angle. Now maybe I made that angle bigger than 5 degrees, less than 5 degrees. I don't know. I'm just going to pretend that that's 5 degrees right there. And I'll leave the 5 degrees up here. I won't try to squeeze it into the drawing. Where am I going to put the B and the C? I can put the B and the C anywhere I want, right? But if C is 125 degrees, I'm not going to connect it over here with this another tiny angle, right? In fact, because I'm given two angles, third angle is automatically filled in. With 5 degrees and 125 degrees, they add up to 130. The remaining angle has to be what? 50 degrees. File that away. If you have two angles, third angle is automatically specified. So if I'm going to stick a B over here, let's cut this off and call this B. I want to make an angle B of 50 degrees. Let me draw off something that might be 50 degrees. And then finish connecting the sides of this triangle. ABC. Sides A, B, C. Opposite each angle. So what do you think? Is there a real triangle here or not? If I've got 5 degrees and 50 degrees here, this is about 125 degrees. Yes, I definitely have a real triangle because these three add up to 180. And because someone told me this is 51 yards, I can now fill in the A and the B. Let's go again to the nearest tenth of a yard. I could pick two decimal places, but I'll go to the nearest tenth of a yard. As soon as I know that I have a triangle, then I could start calculating with the law of sines. So the sine of A, which is 5 degrees, is to A as, what am I going to pick? The C pair right here, because I know both of those. The sine of 125 is to 51, which also matches the sine of 50 to B. So from these two expressions, I'm going to find out what A is, and I'm going to find out what B is. So let's pretend you're cross multiplying. (51) sine 5 degrees is A sine 125 degrees. So that makes A 51 sine 5 degrees over sine 125 degrees. That's going to be some approximation, but I can use a calculator to do that approximation. I'll pull in the calculator. I'm in degree mode. I've been in degree mode all day. You know, doesn't hurt to check, but I'm in degree mode. And so I say 51 sine 5, stop, parentheses, divided by sine 125. Let's see what I got right here. This ought to make sense still, right? So this says 5.4. Let's take it to the nearest tenth, 5.4 yards. Now you're saying that's really small. Well, on the other hand, this angle A was really small. So this is somewhat believable. I mean, I'm not alarmed by the size of that compared to the size of that. I always want things to be realistic, but this looks realistic. Did I draw it so that this is 10 times larger than that? a little bit like it? No, I didn't draw it that way. But it's a believable number. Now let's look for b. Cross multiply. B times the sine of 125 degrees is 51 times the sine of 50 degrees. And that allows me to find out what b is. I say 51 sine 5 degrees over. Did I say that right? No. Somebody got a 50 right here. That's 50 degrees. My fault. When I cross multiply, I get 51 times sine 50 degrees equals b times sine 125. So when I divide by sine 125, I don't get all the same numbers as I did last time. 51 sine 50 over sine 125. That's very close to this, but it's going to be 51 sine 50 stop divided by sine 125. Stop. That's 47.7 yards. Again, that looks believable compared to 51, even if my drawing is not precisely correct. 47.7 yards. I should do one more thing when I'm writing the answer down here. I should tell people I was approximating on that calculation. I was approximating on that calculation. The 50 is exact. Also notice I didn't find out what A is approximately and then use that to find out what B is. I always work from the known to the unknown. So the 51 and the sine 125 are solid, exact, golden. So I used that twice to find the A and B. I didn't use the perfect number to find the approximate number and then the approximate number to find B. Always work from the known numbers to the unknown numbers. Okay, good. Let me try another one. Let's see. There's lots of practical problems you can make here, but what happens? You always have to ask yourself, is this a real triangle, yes or no? So what happens if I gave you, oh, by the way, now that I'm done with that problem, I should tell you where I got it from, right? So in case you want to look it up later, that was problem 6 of section 7.1. So that was one of the early problems. This is a real triangle, no problem. Okay, so I'm going to pick another one out. It's a little bit harder now. Move that off the top and check out the next piece of paper. So let's try something like triangle A, B, C. Again, I'm not going to tell you where I take it from until after we do it. And let's say the angles A, B, and C, I'll give you some of them. And the sides A, B, and C, I'll give you some of them. And you have to decide if I gave you enough to make a real triangle, or if I gave you enough to make 2 real triangles, or no real triangles. Okay, so let's say A is 40 degrees. Let's say B is 62 centimeters. You can use any angle that someone gives you, any units that someone gives you. And let's say A is 54 centimeters. Now, I definitely feel good about the law of sines here. Remember, because whenever I have an angle and the side opposite that angle, that gives me a basis to use the law of sines. Since I know capital A and little a, I know this ratio. and I'll be allowed to compare it to this ratio. I know B, maybe I could find angle B. Or to this ratio. If I learned angle C, so I take this, find angle B. From A and B, I find angle C. From C, I find lowercase side c. So because I have these two opposite pieces of information, I can definitely use the law of sines. The question is, do I have a legitimate triangle? So now let's draw it. And again, you draw it in any legitimate way you like, but I always like to start A lowercase left, A lower left corner. And then I'm gonna lay out the horizon. And I don't know how long I need, so I'll just lay it out and not stop it yet. But this time my crane has been elevated by 40 degrees. Maybe it looks something like that. Now I got to pick my B and C, right? So let's take this angle A, 40 degrees, and the side opposite will be 54. But this side next to it is going to be 62. Now, do I put the 62 here? Or do I put the 62 here? Well, I'm using this idea of a crane. So I'm going to put this side B equal to 62 right here. And imagine a 54-foot rope dangling down. Now, if this angle is 40 degrees and this side is 62 feet long, the crane is 62 feet long, I think it's a good chance. 54-foot rope is nearly as long as the crane. I think it's a good chance that I get to have two different triangles. How would I know for sure? Let's find out how tall the crane is. Let's find out the height of that crane. By the way, as soon as I say the crane is 62 centimeters long, okay, I guess this is a toy crane now because it's 62 centimeters long. I always like to think about the idea of a crane. I think it's really useful, but a real crane is not measured in centimeters. So this is a toy crane. So I'm calling this angle B on the horizon, and this angle right here must be C. So I do not know where to put that B yet. 54-foot long rope seems pretty long. I think I could have a B here or a B here. Let's figure out the H and find out. That's just right triangle trigonometry. H is to 62 as the sine of 40 degrees. Okay. I'll check something right there. Okay, so now I know what H is. H is 62 sine 40 degrees. Now that's not a perfect exact number, but it's going to give me a good approximation. I know approximately how tall that crane is. So let's say 62 times sine 40. Stop. That crane tip is approximately 39.9 centimeters above the ground. But that's an approximation, so I say it's an approximation. Notice that does not fill in my triangle, but it does confirm for me that I have two triangles to fill in. If this height is 39.9, then I think I could drag that 54-foot rope well over here underneath the crane, or swing it out the other way on this side of the crane. I'm not drawing that perfectly. Now what this does is it gives me two B's, right? I could have B right here, or I could have B right here. Both of them have the same side length, B equals 62, but this angle is going to be more than 90 degrees, and this angle is going to be less than 90 degrees. So let's figure out how I'm going to do that. Notice I also have two C's, tiny C and a bigger C. So let's figure out how I'm going to do that. Notice I already have an opportunity to find B right here. So let's write the ratio. Sine 40 is to 54 as the sine of B is to 62. Sine 40 is to 54 centimeters as the sine of B is to 62. Now this is a different use of the ratio because I don't need to know the side lengths, I need to know that angle. But I still cross multiply. 62 times sine 40 is 54 times sine B. And that gives me the sine of B is equal to 62 sine 40 degrees over 54. Now, how do I proceed? I have to use the inverse sine. This B is going to be the inverse sine of 62 sine 40 over 54. Notice I don't plug in and find out the number 62 sine 40 over 54 and then round it off and then take it down here. I'm just going to let the calculator do this calculation. I'm interested in the inverse sine of that number. The sine of B is that number, so I'm interested in the inverse sine of that number. Let's work it out. So I have sine inverse. I know I'm in degree mode. 62 times the sine of 40. Stop. Divided by 54. Then stop the sine inverse. So what does this number turn out to be? This is a degrees, right? This says B is approximately, not exactly, 47.6 degrees. Now let's go back to my drawing. Which of these two angles is 47.6 degrees? Well, it's got to be this outer angle here. But what would that make this bigger than 90 degree angle, right? If that's 47.6 degrees right here, then what's this leftover angle? Remember, this is an isosceles triangle. This would be 47.62. I should say 47.6 also, not 47.62, the number. So what would be this remaining angle? So B could be 47.6 degrees or 180 minus 47.6 degrees. Yeah, think for a second. Whoa, what would that be? 132.4. That's this angle right here. So I've got two possible triangles. I should write that down. I should actually specify two possible triangles. So here, let's put the 47.6. And then let's fill in the rest. And then I'll specify another one over here with the 132.4. So I actually have to give two answers here. And remember, I should say which answers are exact and which answers are approximations. This 47.6 is an approximation. This 132.4 is an approximation. Once I know the 47.6, I can find C, but since B is an approximation, so will CB. So what's the C right here? This adds up to 87.6, and it's supposed to add up to 180. So what's 180 minus 87.6? Maybe I don't feel super comfortable doing that in my head. That's okay. 180 minus 87.6 would be 92.4. But because B is approximate, so is C. What about over here? This is 172.4. What's 180 minus 172.4? 7.6 degrees. But because B is approximate, so is C. Notice that C of 7.6 makes sense in my drawing. And the larger C of 92.4, well, kind of makes sense. I think I made that angle too big, but it's certainly more than 90. Okay, what's missing? The only thing that's missing now is the C. The C. Now notice I have an approximate value of 92.4, so that's going to make this approximate. What do I got here? The sine of 92.4 over C is equal to, let's use the exact numbers, not 47, 6, and 62, but 40 and 54. Sine of 40 over 54. Cross multiply. C sine 40 is 54. Sine 92.4. And then I can figure out what C is. Now, I want to be careful with my 92.4. You know, that 92.4 is an approximation, right? But I actually had the 47.6 sitting right here. So I could add my 40 degrees to this number and take that away from 180 to make that a more perfect number. Let's try that. 40 degrees, I could just arrow up to here. Say add that number. I gotta put an addition sign in between. And then take not 180 minus 87.6, but 180 minus that exact number. And that gives me 92.43. So that's a little more exact to do this calculation. So let's say sine C is 54, sine approximately 92.4, but 92.437, it goes on forever. I'll use that number on my calculator screen and divide by sine 40. Sine 40 is exact. So what does that give me for an approximate value of C? So I'll take 54 times the sine of that number right there. I just go up there and highlight it and grab it. I don't have to retype it. I'll just let the calculator grab it. Then divide by sine 40. That's 83.9. Most precisely, 83.9 centimeters. Okay, I'm going to fill that in, 83.9 centimeters. And it's an approximate value, so I tell people it's an approximate value. The green numbers were exact, the blue numbers were approximate. Over here, I got my 7.6 going on. Where is that 7.6? That 7.6 is from calculating these two approximate numbers right here, right? So where did I get that 132.4? From taking the 47.6 complement. So let's take 40 degrees plus 180 minus that exact value up here, 47.56 and change. I had it up the screen here. That adds up to what? 172.43. Then let's take 180 minus that. Now I got an exact angle for C. Well, as exact as I can take it. And then let's work out what lowercase c is. Sine of 7.6 approximately over C is the sine of 40, use the exact values, over 54. Then we're going to wrap up our calculations for today. Cross multiply, C sine 40, exact value, is 54 times the sine of 7.6, approximate value. So C is 54 times the sine of approximately 7.6 divided by sine 40. Since I got that approximate 7.6 on my screen right here, I can do the calculation without wasting any digits, without taking any compromises. 54 times the sine of that angle divided by the sine of 40 degrees. I have 11.056, rounded to the nearest tenth, that's 11.1. So I have two triangles that can specify this information. Notice that's an approximate. So here are the numbers I calculated, and the A, and B were the numbers I was given. The numbers I calculated were approximate. The numbers I was given were exact. Now, just so you can look it up later if you like, I took this not from exercises, but I took this from example 2 in section 7.2. So here's the case where I have to make a choice. Ambiguous, I have two different answers possible. I have to calculate both answers. Yeah, good question by Austin. I would have to say on the test, do this to the nearest tenth of a centimeter, or do this to 3 significant digits. But I would say if you round off too early and you give me 83.7, and the full exact number is 83.9 to the nearest tenth of a centimeter, then you got to give me the complete number to the nearest tenth of a centimeter. Now, I wouldn't, depends on how far off you'd be, it's like how much you'd be penalized. But I have to specify, the problem specifies the precision, and you have to use the exact numbers as far as you have them to do the calculation. Okay, good question. We're going to do other examples where you see that in action. We have the law of cosines today, law of sines next time. Okay, I'm going to let that be because we're at the end of our time, and I will get these copied and posted so you can play with these some more. But practice drawing these triangles. And if you like, you can follow any way drum you like, but I like A in the lower left corner, horizon, and then I can figure out B and C from that. But yes, literally you could put the letters in any position. Just might make the drawing more awkward one way or another. Okay, you guys dig in, you have fun, and I'll see you again in our shortened Thanksgiving week on Monday. Have a nice weekend there.